Okay, so I have summarized the generators that we've derived so far. These are all of the elements of the Lie algebra. What we want to do now is we want to work out their commutators. Now, a lot of the structure of this algebra follows from a few simple considerations. So I want to start off by just giving a rough discussion of what we expect before we start to get down to the nitty-gritties of actually calculating these generators. So the first thing I'm going to do is dimensional analysis. So look at P alpha. So if you look at P alpha, this is a d by dx alpha. So this is an inverse length. If you look at m mu nu, well, this is an x times by d by dx in both terms. So that'll be length to the naught. And the dilatation generator, the generator of scalings, also looks like an x times by d by dx. So d also is dimensionless. And if we look at the special conformal generator, so the special conformal generator looks like an x squared times by a d by dx. So this will be a length. When we calculate the commutator of two elements of the Lie algebra, we get another element of the Lie algebra. So for example, if I was to calculate the commutator of P alpha with D, well, P alpha is an inverse length. D is a length to the naught. So the commutator of P alpha with D has to be an inverse length. So the only thing that it can be, let me not write equals, the only thing that it can be is P alpha again. And I just wrote that down by dimensional analysis. I didn't use anything else. In exactly the same way, M mu nu, well, that's dimensionless. So if I calculate the commutator with P alpha, which is a length to the minus 1, I must get a length to the minus 1. And the only generator that could appear on the right-hand side is P alpha. And then finally, if I calculate the commutator between P alpha and P beta, well, this is a length to the minus 1, commutator with length to the minus 1. I must get something which is length to the minus 2, and there is no generator that's dimension of length to the minus 2, so P alpha and P beta must vanish. Of course, exactly the same arguments go through for the generator of special conformal transformations. So K alpha is inverse length, D is length to the naught. We must get an inverse length. When we look at the M mu nu is dimensionless. K alpha is an inverse length. K alpha is an inverse length. We must get an inverse length. So we must get something like K alpha. For these M mu nu commutators, the right-hand side is obviously wrong. It's obviously wrong because it doesn't have the right indices appearing. So we must have some extra thing with more indices appearing, and that's going to be eta mu nu. So we'll see that the Minkowski metric starts to appear on the right-hand side, and it'll fix up where all of the indices go. Right now, I'm not being careful with indices, so I'm not taking into account Lorentz invariance. I'm only looking at dimensional analysis. If I calculate the commutator of K alpha with K beta, well, this is an inverse length with an inverse length. That'll give me an inverse length squared, and there is no generator with a dimension of inverse length squared. If I was to calculate the commutator between M mu nu and D, well, M is length to the 0, D is length to the 0. So all that can appear on this side is again terms of length to the 0. So it should be an M mu nu and a D, okay? Something like that. And then another one that we can do, this is the final one, I guess. I may have missed some out, but you can do them. If we've got a P alpha comma K beta, well, what do we get on this side? Well, P is an inverse length, K is a length. So on the right-hand side, we must get things that are dimensionless. And in fact, we can get an M. I know the indices on the left-hand side are alpha beta, so this must be something like an alpha beta. And then I can also get a D. And stick indices in, I should also get something like an eta alpha beta. Okay, something like that. So in the last commutator that I wrote, I was also looking a little bit at Lorentz invariance. But this is what follows just from dimensional analysis. So here we haven't done a computation yet. We just did dimensional analysis, but this is nice. It gives us an idea of what to expect. So this was just from dimensional analysis. So let's say just from dimensional analysis. So this is very cheap, but nice. It already gave us something. Okay. So now let's calculate a commutator. And all of the commutators that we calculate in exactly the same way. I actually like to calculate I times by a commutator. And I'm going to look at the commutator of M mu nu with P alpha. Okay, we're going to act on F. What is this going to be equal to? Well, it's just I times by M mu nu, then P alpha on F minus P alpha, and then M mu nu on F. And now what I do is I just plug the expressions for my generators in. So for M mu nu, I'll have an I x mu d mu minus I x nu d mu. Let me maybe move this down ever so slightly so that you can see that. Then I'll have a minus I d alpha. This is all acting on the F. And then we will have a minus I. And now we have first the d alpha and then the I x mu d mu minus I x mu d mu acting on the F. Now, I want you to notice something. There are some terms where there are two derivatives of F. So from this first bracket over here, let's maybe look at this d nu and this d alpha acting on the F. That'll cancel when this d alpha and the d nu act on the F on the second line. And they cancel because of that extra minus sign. But one thing that can happen on the second line that can't happen on the first line is that this d alpha can hit that x mu. See here, d alpha cannot hit that dx mu. So it's this second term, the d alpha hitting the x mu, that's where all of the commutator comes from. When the two derivatives act on f, they cancel from the first line and the second line. We don't even have to worry about them. So the contribution only comes from the d alpha hitting the x mu. Okay, so on your page, why don't you make a note of where all of the contributions to this commutator come from? And then I'll do it in a minute too. Okay, good. I hope you've done it. So all of the contributions to the commutator comes either when this x alpha acts on that x mu, or the x alpha acts on that x nu. And those are the only terms that contribute. So let's write those down, okay? So this will be, so the minus I times the minus I is a minus. The d alpha on the x mu is an eta alpha mu, and we've got a d nu on the f. That's the first term. Then for the second term, the minus times the minus times the minus is a minus. I times I is a minus, so we get a plus I. D alpha acting on the x nu is an eta alpha nu, and then we've got a d mu acting on the f. Good. And that's what the commutator is. If I was too quick for you, write out all of the terms and see what cancels. So there'll be some terms that cancel from the first line and the second line. And now we just take a look at our generators and we reinterpret this in terms of generators. So eta alpha mu, this is a p nu on f minus I eta alpha nu and a p mu on f. Now we can drop the f and we have our first commutator. I m mu nu e alpha is equal to eta alpha mu p nu minus eta alpha nu. Oh, don't know why that I survived. Shouldn't be there. Minus eta alpha nu p nu. So this is the first commutator that we've calculated. Few comments. We said m comma p had to give us a p from our dimensional analysis. That was that statement over there. We now indeed see m comma p has given us a p. And we said that extra values of the Minkowski metric had to appear to get the indices straight. And you can see indeed we've got two etas appearing. And well, that's the form of the commutator.